First principles is wrong. Sort of. Yes, sometimes it is all about breaking down the problem into manageable parts and tackling them individually, recognizing the unique contribution of each component. On the flip side, there are instances where it is better to abstract away the differences between two things, and finding an analogy can help us gain understanding of the world. We must include in our toolbox abstraction and analogy as well. It's all about choosing the right tool for the job. I'm Zé, a PhD student on computational mechanics. Welcome back to the channel. First principles thinking is very popular these days, mostly because of Elon Musk. SpaceX and Tesla are impressive companies that are pushing the envelope in large part because of Elon. But how does he think?
I think it's also important to reason from first principles rather than by analogy. And what that really means is you kind of boil things down to the most fundamental truths and then reason up from there.
He reasons from first principles. It must be the best way to think. Case closed? Not so fast. Let us look first at Elon's example.
Somebody could say that battery packs are really expensive and that's just the way they'll always be, because that's the way they've been in the past. And you say, no, okay, well, what are the batteries made of? What are the material constituents of the batteries? What is the spot market value of the material constituents? So you can say, okay, it's got cobalt, nickel, aluminum. So break that down on a material basis and say, okay, what if we bought that in the London Metal Exchange, what would each of those things cost? Like, oh, geez, it's like $80 per kilowatt hour.
Okay, so it has to do with producing cheaper batteries. In classic first principles way, he breaks down the problem into its smallest components. In this case, he highlights the materials that make up the battery: lithium, cobalt, and so on. Did you see it? The sleight of hand that makes first principles work? To see it better, let's take first principles to its logical conclusion. Why stop at the different materials? Let's go further. Each of the materials mentioned by Elon in the battery itself is made of individual atoms. We can consider their wave function, or go even deeper and think about the subparticles that make them up. Through a sort of reductio ad absurdum, we have reached the limits of first principles. We have to stop somewhere. How do we choose where to stop? In the ridiculous example I gave, it is easy to see where to stop. Atoms of the same element are for our purposes equivalent to each other. That is precisely because we can abstract away the differences between them. Choosing the proper level of abstraction is fundamental to stop an infinite descent into irrelevant details. As an example, imagine you are describing a city. The relevant details are, for example, how many people it has, how many people commute in and out of the city every day, and so on. You care about the system as a whole, without knowing all about John, Mary, and Sue, their cat, and their dog. Those details are behind the abstraction barrier. Essentially, it is a barrier with a name, behind which you hide the irrelevant details about the thing you are talking about. What remains is the important and relevant details. So, can we use this insight to iterate on Elon's example about batteries and find ways to innovate? Yes! If you think about it, what is the role of cobalt in the battery? Cobalt is used because of the way it keeps the oxide neutral when the lithium ion is taken out. So we can take a step back and select as our abstraction a material that has this property, and not cobalt in specific. Now we can see a way to innovate away from cobalt, since what we need is not cobalt in particular, but a material that plays a similar role in the battery. We can even do this at a higher level. A battery itself is just a way to store energy for later use. We can use that as an abstraction. Are there other ways to save energy for later use? Of course there are. Fossil fuels, a flywheel, or hydrogen, for example. Not all of these examples will satisfy other requirements that we might have, such as CO2 emissions, practicality, energy density, and so on. But just thinking about them might lead to innovative ideas. Abstraction even opens up very interesting modeling opportunities. Let's look at an example from math. I'm sure you've heard about vectors. What do they have in common with functions? At first, arrows and curves don't seem to have much to do with each other. But if you're clever and you choose your abstraction like this, don't worry about exactly what these items mean. Both vectors and functions satisfy them, with their differences hidden behind the abstraction barrier. There is an analogy between them. It is a bit stronger than that. Anyway, whatever you prove based on these rules is equally true for vectors and for functions. These objects are called linear spaces, and include from arrows in the plane to functions to complex numbers and linear equations. Abstraction and analogy is a power multiplier. It can even allow you to innovate by noticing that you can apply ideas from other fields in your own. That said, we must understand very well what is the abstraction barrier we set up. Things will break down when the hypothesis underlying it break down. An example is the analogy between electric and magnetic circuits. Despite physically being very different, there is a one-to-one relationship between the mathematical quantities in an electric circuit and a magnetic circuit, under certain conditions. You can imagine how this makes the design of magnetic circuits much easier for an engineer. However, if you break the contract, the analogy disappears and you start producing garbage. So, as Sanjoy Mahajan explains in his awesome book, Mastering Complexity in Science and Engineering, to tame complexity, we must both divide and conquer, as in first principles thinking, and use the most useful abstractions for our problem.